I welcome everyone for this third part and final part of the three-part webinar series. So today's session is going to be cavitation index prediction. So it's more on control valves and how the cavitation occurs and things. Okay. So in case if you have missed the first two sessions, it was about flow characteristics like CV and CDT, torque coefficient. So those recordings, as well as this session's recording, will be provided to you on. It will be available on the website by start of the next week, and then you can watch those to catch up and brush up things. So I have a lot to cover today, so I didn't include the recap. Usually I do that, but I didn't include the recap of both the sessions. So we'll directly jump into the today's topic. So I'll start with the speaker introduction. Myself, Praveen Kumar. I'm the product marketing manager in Simulation Hub, and I'm basically a mechanical engineer with around 15 plus years of experience in applying CFD simulations for different application areas, including valve and building HVAC and etc. So I recently completed my PG diploma in product management and then moved into product related roles. And with me, I have Akshay. Akshay, please introduce yourself.
Yes, Praveen. Hello, everyone. I'm Akshay. Uh, I'm the business manager of AVC. I have a couple of years of experience in CFD myself. I have a master's degree in mechanical engineering from NIT Silchar. Just recently moved into this role of business manager, trying to understand and learn and solve key business problems of the wall industry. And really excited for this new role.
Okay.
Yeah. How about you,
Thanks,
Praveen?
thanks, Akshay. He's our young dynamic leader. So yeah, so now let's look at the agenda. So first we'll start with introduction about, understand what is cavitation and how it occurs in valves, and what are the different parameters to measure the intensity of cavitation, and how do we determine those parameters or performance parameters? What are the different methodologies available? Then we'll introduce autonomous valve CFD application, and we see some interesting case studies that Akshay has brought to this session. Then we'll end with some real life success stories, and then towards the end, we'll have the Q&A session. So meanwhile, during the session, if you have any questions, feel free to put them in the chat window, and we'll collect them and address those in the end, okay, towards the end. So what is cavitation? Cavitation is nothing but formation and breaking up of collapse or breaking up of bubbles, vapor bubbles, cavities in the liquid, okay, when the liquid flows. And when it occurs, when the liquid's static pressure, local static pressure drops below the vapor pressure of the liquid, then this cavitation phenomena occurs. And most of the damage associated with the cavitation occurs when the collapse of bubble happens. When the bubble collapse, it hits the or the surface and then it erodes. Okay, that is how the damage is caused. So this is general cavitation, but what happens in valves? How it happens in valves? So to understand that, we should understand certain terms like vena contracta. Vena contracta, it is nothing but the minimum area of a flow stream. So where the minimum gap or flow area is, and that is where the velocity will be maximum and the pressure will be lowest. So the minimum pressure occurs at the vena contracta, and when this minimum pressure or vena contracta pressure drops below the vapor pressure of the liquid, then the bubble formation happens. Now downstream the flow, then when the pressure recovers back above the vapor pressure, then the bubble collapse. So here you can see, let me take this. So here you can see the bubble collapse position happening, and then the flashing occurs when the recovery doesn't happen, and it remains below the vapor pressure only. Even the outlet pressure, there is no recovery. It stayed below the vapor pressure, so it's completely choked flow happens. That is beyond choke flow. That flashing happens when the outlet pressure is less than the vapor pressure. Okay. So what are the impacts of cavitation? So first is material damage and noise, vibration, and that collectively causes the flow effectiveness, like that will consume the energy, and the flow capacity, everything starts deteriorating. Okay. So you can see this animation shows how the microjet collapses and starts damaging the surface. So when this prolonged exposure of cavitation occurs, then it causes this kind of damage to the important parts of the valves, either the plug or the cage or the valve body itself. Okay? So what are the methods to combat cavitation in valves? There are four ways you can do that. One is avoid cavitation by elevating your operating condition, operating pressure. So you're operating at such high pressures such that you're far away from your minimum pressure, or vena contractor pressure is far away from the vapor pressure. So there is no risk of cavitation. The other way is like to strengthen or increase the robustness of the material. So hardened material for critical parts of the valve. So that is another way of combating cavitation. The third one is isolating the cavitation. So where the bubble collapse and breakup happens. So that you just design it such a way that the bubble collapse at the not near the surface, it's far away from the surface. So that is one way. The last one is to eliminate by designing the valve to have staged pressure drop instead of one sharp single high pressure drop. So let's discuss more of the about the fourth point. So how staging the pressure drop helps in avoiding or combating the cavitation. So the blue color curve shows a typical or normal where the cavitation happens. The single pressure drop, and then the point of bubble formation and bubble collapse when the pressure recovers. Okay. So this is like pressure plotted along the flow length. So now when we have stage pressure drop, the inlet and outlet is same in both the cases. You modify the design of the valve or flow path such that it doesn't have the single sharp pressure drop, but it reaches P inlet to P outlet in multiple stages. It's a slow or low recovery valve trim design. So how it is done? That in that case, it avoids touching the vapor pressure at all. The vena contractor will not go below the vapor pressure. So how it is achieved? There are multiple designs available. So using a single cage, single stage, multi-hole, and multi-stage and multi-hole. So all these sort of designs are available. It's generally followed. Okay. And then they keep on optimizing these design to achieve the both flow capacity as well as to avoid minimum pressure. Okay, that's the thing. So now we have discussed about cavitation and cavitation in valves and stuff. Now the time is to introduce to certain parameters of that will help you to categorize the intensity of cavitation. So one is cavitation index, the other one is liquid pressure recovery factor (FL). So how cavitation index is calculated? It's like P upstream minus P vapor upon the pressure drop across the valve. So we'll see more details about cavitation index in further slides. So what happens is when I plot the flow rate across pressure drop, square root of pressure drop, you can see a straight line of this curve. So this indicates the CV is constant and Q is proportional to the square root of pressure drop in the non-cavitating zone. So this CV will not remain constant, and this line cannot go extend, in the same direction beyond certain point. It will start deviating. So that is the point, that's like the incipient cavitation. the point where it starts, the CV is not constant, and then the pressure started, the vena contracta starts dropping below the vapor pressure. That point is called the incipient cavitation. And then you can see the curve, and then slowly it reaches the choke flow. Further increase in pressure drop causes choke flow, and then it continues. So the Q will not, when I keep on increasing the pressure drop, the Q keeps on increasing. That is the slope. Slope is CV. CV is constant. That's why the Q is increasing as we increase the pressure drop. But beyond certain point, any further increase in pressure drop will not result in increase in the flow rate. So that is the incipient cavitation and then choke flow. Choke flow is like kind of, it's saturated. The Q is has attained its maximum capacity. The maximum flow is achieved. So that is choke flow. This is the complete graph of, if you see, across the valve, when you keep increasing the pressure across the pressure drop across the valve. So here is a plot comparing, this kind of pressure P1 and P2. Let's say I took different types of valves, and I kept the P1 and P2 outlet, inlet and outlet pressure constant, and then plot this pressure drop across the flow length. Then you can see this the pressure minimum reaches more on for the ball valve, and then the recovery is very high. High recovery is, kind of more prone to cavitation. So that's the comparison part. But don't worry, this is not kind of, this is the typical graph. It's not like universally true. So again, we'll have one more slide. Just just be with me. I'll explain we will debunk few myths in this session. So yes, FL is something to do with, what is the maximum flow it can deliver and when the choke flow can occur. So that FL can be used to determine those. Okay. So how do we get this cavitation index? So what happens is, in the lab, there is no way or method to measure what is your minimum or pressure or vena contracta pressure. Okay. So you cannot, you can measure the pressure at inlet and outlet like 2D and 6D, but in the labs, flow loop testing labs, but there is no provision to measure the P minimum. So you cannot, really calculate the cavitation index by measuring the P minimum in flow loop test. So what they do is they use the accelerometer to measure the noise and vibration, and they plot the cavitation index such that they allow the flow conditions to reach the cavitation point, and then they start plotting this accelerometer output against the cavitation index. Okay, so what happens is, so at one point there is a sharp gradient or slope changes. So that point is like incipient cavitation, and beyond that, then constant cavitation occurs. Then the choking cavitation occurs. So incipient cavitation is like starting of small bubbles forming in the flow stream. There is no big damage or anything. But beyond this point, then constant cavitation occurs. A small vibration, steady popping happens. And then the choking cavitation, the flow rate doesn't increase beyond this point. So that is choking cavitation, right? So one thing you need to understand is the incipient cavitation index is the uh, key has a key role to play in this case. So once we know the incipient cavitation index from the graph provided by the lab reports, then we can start dividing the operating cavitation index sigma in two categories. Whenever my sigma falls below this incipient cavitation index, then I'm entering the cavitating region. Whenever my cavitation index sigma is above this incipient cavitation index, then I am in the safe zone, operating in the safe zone. Okay. The higher the sigma, or the farther the sigma from the incipient cavitation index, the more safer I am, operating in the safer non-cavitating zone. That's what it indicates. Now, there are two questions. One is, you might have come across whenever you search about cavitation index recommended range. So you typically see this kind of tables and colors and plots. Okay. which says sigma is when the sigma is greater than 2, there is no cavitation. And then there are different ranges provided. Okay, though it's like that. So is this really true? Always. Actually, it is not. So sigma, if you see, to calculate sigma, you do not, it doesn't have anything to do with your valve design per se. You know the operating condition, you can calculate the sigma. So look at the formula. So the vapor pressure is same. The P upstream, once you know P upstream and downstream, you can calculate the sigma. This has nothing to do with the design or cavitation and things. So this will be useful to compare this sigma against your incipient cavitation index. Okay, so sigma less than 2 or greater than 2, that doesn't signifies anything. These are typical numbers. This may not be true. This need not to be true always for all your designs or all opening. One more thing I want to highlight. So this graph is for one valve position, valve opening position, keeping the P upstream constant. Okay, so once you achieve this sigma I, then you can compare it with any sigma, any operating pressure or any upstream pressure using this calculating the sigma. Okay, so to summarize, you take this sigma I, incipient cavitation index value, and calculate your sigma operating cavitation index for your operating condition. Compare it with the sigma I. If it is less than incipient value, then you are entering the cavitating zone. If you are operating above the incipient value, then you are safe. So that's the summary of it. Okay. Okay. So we have brought some cases. Let's say I said, sigma, higher the sigma value, it's better. That's what I said, right? But you just, no, please note that I am talking about sigma. But when I compare two designs, should I compare cavitation index or incipient cavitation index? How do I design which valve design or cage design is better? Here I cannot compare cavitation index. Sigma I cannot compare because it is related to the operating condition. Incipient cavitation index is what I need to compare. The lesser the incipient cavitation index, the design is better. Why? The lesser means then the red color graph, the red color portion of the graph reduces, goes towards the left side of the plot, right? So that's why when you compare two designs, valve designs or trim design, you need to compare incipient cavitation index rather than cavitation index. Cavitation index doesn't make sense here. So that's how it is. Okay. So the valve manufacturer provides is supposed to provide cavitation incipient cavitation index for each and every opening of the valve for every size and step. Okay. So I'll explain what happens in a new product development. So I think the fundamentals are set now. So I can press the pedal and accelerate into the topic of what are the different methods and what are the pros and cons. So we saw the flow loop test method, how it is calculated. So now, before going into the pros and cons, we want to understand what is the process. Then we'll be able to understand what are the pros and cons of this method. So what happens in a new product development is a design requirement comes up. Uh, let's have with a target CV or incipient cavitation index kind of, right? So then the designer, with his past experience, with his or her past experience, designs the valve and creates the prototype, manufactures the prototype of the valve, and then the prototype is shipped to the some remote location, remotely located flow loop test facility, and then the test is conducted based on the ANSI ISA standards and M49 standards, and then they provide you with the report, performance report. So typically, if I do not include manufacturing prototype time, then it takes weeks to months. If I include prototype time, again, it goes to 3 months, 2 to 3 months of time. Okay. So at the end of this, let's say you do not achieve the required target CV or cavitation parameter, then you have to follow the same path again, same time and cost involved. But This time you do not have any clue what went wrong with your first design, because all you got is the final values, but you do not have any flow insights what went wrong. It provides you with the final report, the table. Okay, so that is one challenge. So let's look at the challenges in flow loop test. As I said, it provides you with limited flow insights. You cannot visualize what is happening, where the flow separation is happening, where the cavitation is occurring, where the pressure goes below the vapor pressure. So those idea you will not get. Okay, so any design changes cost you more time, and time is money, to that part. And then resource limitations, like for to test really large size valves, the test facilities are limited by how much they can handle. Okay, so what are the other methods? One is analytical and numerical method. So here, analytical method, the time and cost, of course, it's less, but the accuracy is not up to the mark. And for numerical methods, the accuracy is very close to the reality, but the skill and time is, of course, considerably less compared to the flow loop test. But the skill set required to operate and get a meaningful, result out of it, so that is a bit high. So these are the challenges of analytical methods. It doesn't consider the local physics phenomena, like what happens, flow separations and turbulence happening locally due to the trim design. So those things are not considered. So empirical adjustments are done. So that's why it's not accurate. Okay. So the numerical method, CFD, it's nothing but solving governing equations in discretized form in something called cells. Your fluid volume is divided into some shapes, defined shapes, a discrete form. So that is nothing but cells. So like this cubes. So I'm putting it in very layman term to understand. And this numerical equation, or the governing equation, Navier-Stokes equation, is solved in a numerical form, discretized form, in the discretized elements in the form, in the fluid volume. Okay. So this CFD, how it, what are the process? So it starts with the CAD model, and then fluid volume extraction, meshing, turbulence models, a numerical setup, boundary condition, and then the simulations are run on the computer, high performance computing machines, and then you obtain the results at the end. Okay. So the challenges in the CFD, conventional or generic CFD, it's very manual intense process. It involves high performance computing resources in-house, and licensing costs and etc. Okay. So to address these challenges of conventional CFD, we developed autonomous valve CFD. So we call it, it's a virtual flow loop testing application, meaning it mimics the actual flow loop test procedure by following these standards, ANSI-ISA 75.2.2.1 standards, and some part of M49 manual to calculate, formulas and things. So all these things are followed to calculate the performance parameters of a valve. CV, CDT, a loss coefficient, and cavitation index, incipient cavitation index. So here I'm talking about incipient cavitation index. Okay, okay. So this application is powered. It's a cloud application, cloud-based application. So it is powered by Autodesk Platform Services to handle the CAD and post-process or visualize the results on the browser. And AWS, Amazon Web Services, is utilized for running the simulation, CFD simulations on the cloud. So your local machine is not used for running the simulation. Okay. Once you submit, it runs on the cloud. And then the open form is the solver, CFD solver, which is used in the backend and wrapped up in simulation of APIs. Okay. So moving ahead, to simply put, what happens is you provide certain inputs, like you upload the CAD model, select the moving parts, and select the flow direction. So these are the inputs you provide. What the app does is it does the CAD cleanup, mesh generation, CFD simulation autonomously on the cloud. And what it provides is with three set of outputs: 3D visualization, flow inside results, uh, curves like quantitative data, and consolidated PDF report. So to simply put, like, you need minimum set of inputs. It goes into the app, and app provides you with uh, typical CFD output, as well as like velocity contours, flow lines, pressure contours. So these will help you to identify the flow separation and change the design and play with the design. And along with the performance data, cavitation index, CV, and other performance parameters, and everything consolidated in the final report, CFD report. So these are like recently we have added certain features to specifically handle uh, severe service control valve and very anti-cavitation complex trim designs basically. Okay. So additive manufactured trim designs can also be handled using certain features that we have added in the recent version. So without further ado, like I'll hand over the session to Akshay. He'll walk you through the application workflow, and then we'll meet again for the validation studies and success stories. Yes, over to you, Akshay.
Thank you, Praveen. That was a very insightful introduction and dive into the topic of cavitation and incipient cavitation. For a second, I thought I was an attendee to the webinar.
Oh my God. Okay. Thanks. Yeah.
I'll just share my screen. Is my screen visible?
Yes. It's
Okay, great. So let's start with the demo as we do in the past webinars as well. So it will be just a quick introduction to the application and its user interface. So this is the dashboard. We just started our new simulation by clicking the create simulation button. We gave it a name, we gave it a brief description. So today, since we are talking about the incipient cavitation and cavitation index related topics, we chose to demo a globe valve. So this is a globe valve of size DN150. It also has a anti-cavitation trim. So once the upload is done, we move to the selection of moving parts. We select the plug. Everything is pretty standard. So even the motion is specified by the axis of lift, which is again, you just have to click the shaft and it will automatically get the axis. Again, you just have to specify the travel, maximum stem travel, and the openings will be created automatically. Here, we introduce you to the advanced mesh refinement option as well. Since this is a anti-cavitation trim, there is a chance that it might have features that might be very essential to capture. So to have that capability in the meshing, we have added this option. So you just have to select the body and give the appropriate size of the mesh. Rest of the steps pretty easy. Just select the inlet and outlet pipe for specifying the direction, and we just submit the simulation. So essentially, it's the same as the usual AVC workflow. You upload the CAD, you specify the moving parts. Additionally, you can also specify the features that might require additional mesh refinement, and you select the flow direction and you submit the simulation. Once the simulation is submitted, the autonomous CFD workflow takes care of running the simulation and post-processing the results as well. So once the simulation is done, you can visualize the results such as flow lines. Right now we are looking at flow lines. It's an interactive 3D environment which is powered by APS. So you can toggle with different openings. You can visualize velocity, you can visualize pressure. Same thing, you can go for different visualizations that we have. So, okay, it's a bit stuck. Just give me a second. I'll reshare it. Seems to be an issue. Okay, there we go. So sorry for that. Okay.
Okay,
Getting.
let me check.
Okay, okay. Yeah, it's playing now. Yeah, so seems like an issue. Praveen, can you just share
Yeah,
your screen,
I'll
please?
check my
Thank you,
my.
thank you.
Just give me a minute. I'll see. Yeah, it's working fine at my end. Let me share my screen. So, uh, share screen. Okay. So I hope you're able to see my screen now.
Yes.
Just give me a minute. The percentages. Okay, so we're around somewhere around here, right? Like once,
Yeah.
yeah.
Yes. So we are visualizing contours now. Acha, okay. Streamlines. We can increase the speed of the animation. We can change the variable that we are viewing. Uh, so we can even change the angle at which, sorry, the lift of the plug as well.
Yeah, I'll
So
slightly
that's
increase
pretty
the.
cool. Yeah. We can even visualize the surface pressures. So this becomes very essential in, with today's topic. So we are, actually looking at the regions of minimum pressure. So this becomes a very good visualization feature. And we have velocity contours. So you can visualize how the flow is actually taking place in the fluid domain. So apart from the qualitative data, we also have quantitative data. So we can see what the CV is in terms of tabular form, also in terms of the graphical form. We provide three graphs: CV, KV, and head loss coefficient, and a consolidated view of the qualitative as well as the quantitative data is seen in this report that is automatically generated after the simulation is completed. It has the brief introduction to the CFD workflow, to the assumptions in the CFD, the various data that we calculated, and we also have the incipient cavitation index. Again, this is provided as a table. We mention the operating pressure and the minimum pressure.
Okay.
Yeah. Uh,
You want to take it back? Screen
sure,
sharing.
sure. I can take it back. Thank you, Praveen, for that assist. Uh, so let's jump into the case studies that we did for this session.
Yes.
So we'll start with understanding the effect of outlet pressure. So as Praveen mentioned, for any valve, what we can do is evaluate the operating cavitation index, which is basically determined by your upstream and downstream pressure and the vapor pressure of the fluid medium. So this is exactly what we did. We fixed the inlet pressure and we fixed the outlet pressure for the first condition on the extreme left. And we found out that the cavitation index was 9. And then we started reducing the downstream pressure. So when we move to the next one at 4 bar downstream pressure, we see that the cavitation index drops from 9 to 4.26, and we drop it further to 1 bar, and we see that the cavitation index is 1.78. Now, the interesting part to note here is that the minimum pressure here is well below the vapor pressure of the fluid, and this means that the valve is cavitating. And in the middle case, where it's just touching the minimum vena contracta pressure, so the what here we have to understand is the incipient cavitation index is a constant for the particular valve opening and for the particular size of the valve, but the operating cavitation index might be different. So this is what we saw here. We'll move to the next study, which is we did some interesting case here. So what we did is we took one CAD, which one model which has a single valve, and another which has a valve in series. Now I would like you guys to let me know which is the valve that you're expecting to cavitate earlier or later. And I'll just wait for like a couple of like 30 seconds or so just to get your views on this.
So you can enter either one or two, like case
Yes,
one or
one would
case two.
be, yes, one
Yeah.
would be the single valve, second would be the valve in series.
Come on, please.
Yeah.
That will be like the active participation in the session. That will be really
Yes.
okay. Maybe
Okay.
we'll start
Yes,
this, and then there are further case studies. Again, more chances of this interaction.
definitely,
So
definitely.
yeah.
So what we found out is the incipient cavitation for the first where the single valve is present is 1.8, and when it's in series it's 1.64. And why? Again, here we have maintained a constant pressure drop of 1 bar across both the cases. So inlet to outlet, both are at the same pressure difference, and this leads us into the strategies of avoiding cavitation. So as you can see from the plot here, what we have done is we have plotted the pressure across the line, and we see that in the first case, the blue curve where it's a single valve, there is an abrupt change in pressure, and this leads to chances of cavitation, higher chances of cavitation, and which can be seen from the incipient cavitation index of 1.8, which is higher than 1.6. So this is perfectly aligning with our understanding that you know if the cavitation is higher in, you can say, a comparison, then it is more likely to cavitate earlier. When walls are in series, the pressure drop, the same pressure drop of 1 bar, has two stages to the more time, more areas of pressure loss to get to the same downstream pressure. So we can even see in the line plots that instead of abruptly dropping to a very low minimum pressure value, it drops gradually in both the stages. And this could be one of the strategies of mitigating cavitation in your valves. The, you can say, downside to mitigating cavitation is the CV. So obviously we have added an extra pressure consuming device here from 1 volt to 2 volts. So obviously the CV will be hampered, but you protect your walls pretty well. Instead of having an abrupt change in pressure to a minimum pressure, it's a gradual, so it
Yeah.
increases the life of your walls.
Actually, sorry to interrupt.
Yeah.
I have a question from before taking the question. I would like to Thanks. Swapnil answered case two, and that's bang on. So
Thanks,
thanks.
Swapnil.
Participate more. And then I have a question from Naveen, which I felt very relevant, and we need to resolve it right now so that further
Yes.
sites are very. So the question is, cavitation index should be minimum or maximum for a valve? Okay. So I'll take this question. Naveen, I'll just again specify. So there are two terms, right? Incipient cavitation index and cavitation index. So incipient cavitation index kind of it's stamped for that particular design and opening. Okay, so that is constant. Cavitation index is a operating related to operating condition. So if you want to compare two designs, you always compare incipient cavitation index, and that incipient cavitation index should be less. Okay, uh, why it should be less? Maybe I'll use this graph. Akshay, if you can go back to the very previous slides. Sorry,
No issues, no issues. I'll just
just hold on to the information. Oh, okay. So should I share the screen?
just a second. I guess I'm there.
Yeah, one once.
This
Yes,
one.
this graph, and then click once. Yeah,
Yes.
yes. So you see the incipient cavitation index. If it is less, then the red color portion cavitating zone is also less. Okay. So when you want to compare two designs, you compare incipient cavitation index. So the incipient cavitation is index is less, then the design is better, and the P minimum is more, and so on. Having said that, I'll clear one more confusion also. Given a design, given an incipient cavitation index, within for that one single valve, okay? Now you want to compare two operating conditions. For which operating conditions it will fall where? Then, then cavitation index comes into picture, sigma, not the incipient, okay? So now you calculate the cavitation index for that operating condition, and you just see, okay, the lesser the cavitation, then more closer you go towards the incipient, towards that line, then that is a problem. So it's reverse, incipient cavitation index should be lesser, that is better. Operating cavitation index should be max, should be higher, that is better. So these are the things. And when you have one single design and you want to compare two operating conditions, compare cavitation index sigma. If you have two designs and you want to compare which one is better, then you compare incipient cavitation index. Okay, I hope that is clear. So I guess this will help to understand and enjoy the further case studies. Yes, yes, Akshay. Sorry, that took some time,
Yes.
but I thought
But no,
it's
that was very uh, relevant to the discussion we were having. So
yes.
thank you, Swapnil, for that. So yes, just concluding this particular case was you protect your valve by adding more stages, but the downside is you know you have lesser CV, but in the long run, this should be good for you. Again, a time for a question for you guys. So we have two cases. It's an orifice plate. So the top one has a single hole. The bottom one has 17 holes. The interesting point is in both the cases, the area of the hole is exactly same. So again, I would like to throw this question to you and let me know your opinion. What should be the incipient cavitation index? Which one do you predict has the higher incipient cavitation, or which one is likely to cavitate first? I'll just wait for a few seconds. Praveen, do let me know if we have any
No, okay, I got one entry. Case 2 should have lesser cavitation index. Yes, Naveen, I guess now I can confirm you got the understanding. Okay, let's see, let's see.
Yes.
I don't want to discuss. Yes, we can
Thank you,
actually
Naveen, for that. So
yes.
yes, you were correct. Case 2 has a lesser incipient cavitation index as compared to case 1. And this is,
While answering, I guess he typed it as lesser cavitation index, but I'm assuming he means incipient cavitation index. Yeah, so
yes, yes,
that is
yes.
always confusing. So I just want to bring that point again and again. Okay. Okay.
Yeah, yeah. So again, this is fairly straightforward as well. So whenever there is a small opening and there is a larger chance and a larger, you can say, a magnitude of pressure drop, and a single hole, in a single hole case, the pressure drop happens across very abruptly across that single hole. When the same area is spread out over multiple holes, the pressure drop is gradual. That means, the as we saw in the previous slide, instead of the pressure dropping abruptly, it happens gradually across the holes for the same plate thickness. And that is exactly what we see in incipient cavitation index as well.
Yes.
So
I'll add one more point. Let's see if that brings confusion, more confusion or clarity. So in this case, we have maintained in both the cases same upstream pressure, same downstream pressure.
downstream pressure, yeah,
So what will happen to sigma operating, cavitation index, not the incipient one. Incipient one is right in front of you. It's lesser and better in case two and higher in case one. What
yeah,
what is the state of cavitation index? Both upstream and downstream pressure are same in both the cases for both the designs.
yeah,
What is the sigma? It is same. Sigma is
exactly.
same. Sigma has nothing to do with the design per se. Whether design one, design two, it has everything to do with the operating condition. When your operating conditions are same, the sigma is same. You cannot decide just based on sigma, not the incipient sigma.
Yeah,
You cannot decide whether it will have, which one is better or anything. Okay, when you compare two designs, you need to compare incipient cavitation
incipient
index.
cavitation index.
Sigma has
Just to
no relevance. Sigma, you compare the sigma with sigma I, then you can say that particular design is cavitating or not. That's the thing. Yeah. Okay. Sorry. That's
No
it's
issues, no issues, Praveen. Just to take this analogy further, imagine, like, there are two valves or two different designs of valves. They are exactly at the same upstream downstream pressure, and you wanted to check whether which design is better. In that case, if you move with operating sigma or the operating cavitation index, then it becomes very tough for you to judge because it will be same and you cannot get insights. But incipient cavitation index will give you that insight, whether design 1 or design 2, or you can have any number of designs, which one is better. So yeah, just taking that point that Praveen mentioned. Moving to the next case that we did. So yeah, again, impact of multi-stage hole cage. So sorry, multi-hole cage. So taking the insights from design case study 1 and 2, or I should say case study 2 and 3, which is adding more stages is good for us. And instead of adding two walls in series, we can have, let's say, just the orifice plate, curved it around the plug, and we achieve both of the effects in the same design. So this is just a quick comparison for you. We did the same simulation. So the valve is open for the same, you can say, stem travel. Again, pressure drop is maintained across, the valve is 1 bar. And we have a look at how the trim design will impact the incipient cavitation, or the, how it will help us to mitigate cavitation. And we actually see that. So what happens is P minimum in the case where we have no anti-cavitation trim, it's lower. So again, the pressure is dropping abruptly. And when we add the cage, so because of the cage, it goes down gradually in stages. So right now it's a single stage. So it goes in an additional stage down. And as observed from the previous case studies as well, to compare two designs, we need to compare incipient cavitation indices of the two designs. And that is exactly what we see. We see incipient cavitation for the no cage design is more, and the with the cage design is less. And this is exactly what we were expecting while designing the trim, and we got those results as well from the CFD. So that's great. The only downside to adding the trim is again CV, but in the long run, protecting your walls is much more important than you know you know having more CV, but it might not have the longer life. So moving on to validation study, I would like Praveen
Yes,
to
I'll share.
yeah.
So while I'm sharing the screen, extending the point of Akshay, yes, CV is slightly compromised when we go for avoiding the cavitation part, and that's where CFD comes very handy. Like these tools will help you to optimize the flow path to balance flow capacity as well as avoiding the pressure and stuff. So that will come handy. So I'll present you certain, based on the demo cases, you might have seen how smooth and seamless the workflow is. So, but what about the accuracy part, right? So I'll present you with the validation studies. Akshay, can you confirm my screen is visible?
Yes, Praveen.
Okay, okay, great. So let me take my yes. So what we have done is we have compared. We have done number of validation case studies. We compared a lot of test data from FCRI Kerala and Utah Water Research Laboratories US, and we have considered range of valve sizes and types. So in flow capacities, very less to large, like which means large size valves, as well as all type of valves like globe valve, butterfly valves, and all types of butterfly valve, ball valve, so etc. So what we have observed is we consistently fall in the range of plus or minus 5% deviation, our CFD results. Okay. So to simply put, it's like 90% accurate, but actually it's like plus or minus 5% deviation is the thing. So, and again, particularly if I talk about incipient cavitation index, we have done exclusive validation study based on some experimental data presented by William Remer and Kane. So this is based on a orifice plate, sharp edge orifice plate. So again, you can see the lab data. So accelerometer output. So here, the dotted, if you join it with the straight line, you can see the straight line takes the, change of slope. So each point indicates this is incipient cavitation, constant cavitation, and choking cavitation. So this is the incipient cavitation index, like 2.5 or something. So that was the comparison. So test data says 2.68, and then ours is like 2.49. So 93% accurate. CV is very close, and FL we extended the study to go towards liquid pressure recovery factor. So there we got very close values. So these are 2D cases and it's like very highly mesh refined and things. So if time permits, I will present the FL. Otherwise, we'll conduct another session on FL. I guess we are already running out of time. We'll see how to do that. Okay. So how we do this, how we are able to match the accuracy part, plus or minus 5%. So because at the back end, we follow all the standards, like to measure the test procedure and flow equation formulas. So M49 manual, and on top of it, we also follow verification and validation, VNV 20, ASME VNV 20. So in terms of meshing and setup and all numerical stuff. So what happens behind the scenes is like it does the algorithm does all the cat cleanup. It fixes the gaps and does the meshing autonomously. You can see, there are coarse mesh in the pipe, and then when we go towards the trim or the main core area valve body, it against one level of refinement, and then again near the moving surfaces there is another additional refinement, and near the surfaces there is prism layers to capture the boundary layer. So these kind of mesh refinement again, it once the mesh is generated, it does the mesh check. When the quality is not up to the mark or any failures are achieved, failure is observed, then the algorithm does the mesh refinement, does some quick fixes to improve the mesh quality, and then goes to the solver. So all these things happen autonomously. Again, on the solve part, the residual convergence and pressure monitoring, everything happens autonomously by the app itself. So 2D, 6D pressure tappings are monitored, and then there is a Y plus check. So additionally, for safety engineers, they'll know what I'm talking about. So it does it does takes care of all the checks and improves, make ensure it takes necessary fail safe things and steps to avoid inaccuracy and failures. Okay. So I'll present one interesting case today. Just the like at the towards the end of the session, we are nearing the end. So how we are able to reduce the time to market. So before we started developing this product, we ourselves were providing CFD services using generic CFD tools like Ansys. Okay, so that time what happens is we had to simulate and find out CV value for a control valve with cage design. So that time it took us 7 to 10 days, and even accordingly the time and money part, then quotation was higher. And then now the same design we are able to complete in 1 hour. Okay, so that's the magic of the Autonomous Valve CFD app. How it is possible? Because if you see what happens behind, so for one opening and position, so each opening position has a 36 core Amazon EC2 instance machine assigned to it, and all the process cat cleanup, meshing, solve happens. APIs are called and then happens on the cloud, and then the results are available on your local machine like browser. Through browser you can view. So it calculates all the this should be incipient cavitation index. So all these things are shown to you, delivered to you. Now the same thing happens for all percentages. It doesn't go in queue. In generic tools, like due to license limitation, what happens is when your 1% opening simulation runs, the other goes in queue. Okay, so that doesn't happen here. So all these opening percentages are run parallelly. Each opening percentage has a 36 core machine, dedicated machine running on all the process, CFD process, and at the end of 1 or 2 hours, you will get the complete CV curve or CDT curve and whatnot, right? So it's not just ends there. Let's say you have multiple design options and you want to iterate it quickly. So you can do that, and there is no dependency between the machines because it's a cloud, it's expandable cloud computing facility. So all these designs run, parallel. So okay, again, seamlessly across the globe, your team can collaborate and run simulations on the cloud without any limitations on the number of licenses or things. So it's a small comparison. I'll just accelerate it. So manual versus autonomous process, how much time it takes, and blah blah blah. And then this we have already seen. This is customer success story. So these are our customer list of customers across the globe who are currently using the application and benefiting out of our solution. So recently we have a recent customer win, Flowtite. They're US-based company, and then a lot of much more in pipeline. And then I'll talk about Bray, one case. Bray is a big manufacturer in North America. So they have many centers across the globe, design centers in Houston and Bangalore as well. So their challenge was the time required for flow loop test, and then they already had have generic CFD tools, and they were limited by the number of licenses, one, and their CFD experts were overworked. So the design engineers have to wait in queue to get CFD experts and the license, to be free. And then after the waiting cycle, it takes 5 days to get the complete CV curve or cavitation. So for complex cases, it goes even huge. So after adapting our solution, this time reduced to 1 hour, 2 hours. So now what happens is the CFD experts are free to do their complex simulations like erosion and noise. So those kind of complex simulations, very high mesh counts and stuff, and design engineers, they are equipped and empowered with the easy to use tool, and they are using this tool for a quick design evaluation and do the optimum optimization at their end, and then final submission goes to the CFD experts or flow loop tests. So that's the success here. So the growth of CFD usage has increased from number of users has increased from 3 to all 30 design engineers started using our application and benefiting from CFD simulation. And the total number of simulations are also increased tremendously, and it has saved cost only. And because it's a cloud-based application and web-based application, the even during the COVID period, their team collaborated and they were able to deliver or time ship the new product with anti-cavitation noise and so our association, we conduct a lot of trainings and we frequently meet and understand their pain points, improve the product to improve the experience, user experience. So these are some kind words from Brindesh. So again, there are different success stories like Delval, how they transformed from a very 300 valve simulations and 1500. Now they are even crossed this, and then how they have simulated large size valves and quickly do optimization. Another case study, another success story from plunger valve Magwen, large size plunger valve they have delivered, and we are the simulation partner. So what's next? You can start with a trial subscription, 15 days trial and 20 simulation credits, or even better, you can schedule a call with our expert. And for the webinar attendees, we will provide increased trial period and number of simulation credits, like 1 month, 30 days, and 30 simulation credits. You can do 30 valve opening simulations, CFD simulations with this. And we'll also provide some exclusive discounts for those who would like to proceed further with the subscription. Okay. Okay. I guess thank you. We have just crossed the scheduled time, but again, we can take more questions if any.
Yes.
So
Praveen, there's one question from Naveen.
yes.
So the question is whether incipient cavitation index can be only calculated through testing or simulations, or any standards to calculate incipient cavitation index for different types of trim designs like
Oh, okay.
multi-path single trims.
So there are calculation methods available, but they are again, limited by they cannot capture too many flow paths. Now, with the help of additive manufacturing, the flow paths you cannot imagine. I'll go back to the those slide. I'm hoping you're able to view my slide. Just give me a minute. Yeah. Okay. Sorry. See, how
Yeah.
do you calculate, the incipient cavitation index or using for this those formulas, and they have limitation. So it's you need to adapt to the flow loop tests or much better CFD simulation. That gives you flow insights, deep insights to look into what is happening inside. Okay, and optimize your flow path. So manufacturing is no more a limitation. Now your imagination and things, and soon the AI is coming again. So that will optimize your design, generative, designs. So things are in. I guess it's time to adapt. So although to answer your question, coming back to your question, there are calculation methods, but for simpler geometries and simple flow paths and standard shapes and things, but the world is not stopping there; it's going ahead. So we need to we need to adapt and look for tools that can cope up with the design advancements. Yes. Yeah. Any other questions actually? So I thought I'll get some time and I'll go through certain things. So this August issue of Valve World magazine, we got our technical publications, published on technical article published on Valve World magazine. This edition was purely focused on severe service control. So this topic was very relevant and actually, in fact, this work was presented in Valworld, Germany last year. Again, this presented in as a Word article to read. So digital copy is freely available. You can go to their website and read the digital copy. And I'll try to arrange another session maybe in future to cover what is how you can calculate fluid pressure recovery, liquid pressure recovery factor, FL. So what are the different methods and things? So considering everyone's time, respecting their time and they're joining late and different time zone. So I'll not be able to cover this now, but we'll see. We'll soon arrange another session for this. But meanwhile, you can go through the Valve World magazine, August edition. So yeah. Thanks everyone for staying this late, and even we spilled out of our scheduled time. Still, 10 minutes more, Still, I see a lot of attendees are there. I'm really happy to see that. Thanks for your time. Please feel free to write to us, and we can connect and discuss if you have any questions and queries specific to cavitation or anything related to valve. We'll be happy to have that conversation. Thanks, everyone.
Thank
Thanks,
you.
Akshay, for bringing those interesting case studies.
Thank you,
Uh,
Praveen, for this insightful webinar series that we did.
yeah, that brings down, that's the end of the webinar series.
Yeah,
So in future, we are planning something even bigger. So these are webinars, and it's kind of, it's more one way, and Q&A provides some certain way for two-way interactions. But we are planning live workshops. So in the future, so more about that. Stay tuned. Follow our social media handles. We'll provide more insights about those. Uh, thanks for
thanks, Chandrakant.
thanks, Chandrakant. Okay, thank you. Bye bye.